When we look at the world around us, everything appears solid, tangible, and undeniably real. Objects have shape, weight, and texture. They move, collide, and interact in ways that feel intuitive. But as we probe deeper, far beyond what our senses can perceive, this familiar picture begins to dissolve. What we once thought of as things starts to look less like physical substance and more like patterns governed by precise relationships. And those relationships at their core are mathematical. In modern physics, the fundamental description of nature does not begin with objects, but with structures, abstract frameworks that encode how different quantities relate to one another. Instead of asking what something is made of, the more meaningful question becomes, what equations does it satisfy? A particle, for example, is not simply a tiny billiard ball moving through space. It is better understood as an excitation of a field, and that field itself is defined by mathematical rules. Its behavior is not arbitrary. It follows from symmetry, consistency, and logical necessity. This shift in perspective is subtle but profound. Mathematics in this context is not merely a language we use to describe reality. It begins to look like the very fabric from which reality is constructed. The distinction between description and existence starts to blur. If every measurable property of a system can be captured completely by mathematical relations, then one is led to ask whether anything beyond those relations is required at all. Consider how physical laws are formulated. They are expressed as equations that remain true regardless of where or when you apply them. These equations are not derived from observation alone. They are constrained by deeper principles, symmetry being one of the most important. Symmetry, in a mathematical sense, refers to transformations that leave certain features unchanged. The laws of physics respect these symmetries, and from them, entire structures of interaction emerge. What we interpret as forces or particles can often be traced back to these underlying invariances. This suggests that what we perceive as the richness of the physical world may arise from a comparatively simple set of mathematical rules. Complexity, then, is not fundamental. It is a consequence of structure unfolding from these rules. Much like a fractal pattern generated from a simple formula can produce intricate and seemingly organic designs, the universe itself may be the result of mathematical consistency playing out across different scales. At a deeper level, even the notion of substance becomes difficult to define. In classical thinking, matter was something that existed independently, occupying space and persisting through time. But in quantum theory, the idea of a definite object gives way to probabilities and amplitudes, again, mathematical entities. What we observe are outcomes of these underlying structures, not the structures themselves. The equations do not describe something else. They are the most complete representation we have. There is also an unexpected coherence in how different areas of physics converge through mathematics. The same mathematical ideas often appear in seemingly unrelated contexts. A structure developed to solve a problem in one domain might reappear as the key to understanding something entirely different. This is not what one would expect if mathematics were merely a convenient tool. It points instead to an intrinsic unity, where the consistency of the mathematical framework dictates the form of physical reality. One might then ask, if mathematics is so central, why does the world appear physical at all? The answer may lie in how we, as observers, interact with these structures. Our senses and cognitive processes are adapted to a certain scale, where the underlying mathematical nature is hidden behind emergent phenomena. We do not directly perceive equations, we perceive their consequences. The solidity of a table, the flow of time, the continuity of space, these are effective descriptions, useful and accurate within a certain domain, but not necessarily fundamental. As we move further into regimes where intuition fails, extreme energies, very small distances, or the early universe, the mathematical description becomes not just useful, but essential. Now, in these domains, there's no alternative picture that relies on familiar concepts. The equations are not approximations of reality, they are reality in the most precise sense available to us. This leads to a remarkable possibility. If the universe is entirely governed by mathematical structure, then its existence may be less about material composition and more about logical consistency. In other words, the universe exists because it is a self-consistent mathematical system. There is no need for an underlying stuff beyond that system. What we call existence could simply be the realization of a coherent set of relations. Such an idea challenges deeply held intuitions. It suggests that the ultimate nature of reality is not something we can touch or see, but something we can only understand through reasoning. Yet, in another sense, it is not so alien. Mathematics has always had an uncanny ability to reveal truths that are later confirmed by observation. Its effectiveness is not an accident, it reflects a deeper alignment between thought and reality. If this perspective is correct, then the boundary between physics and mathematics is not as clear as it once seemed. They are not separate disciplines, but different aspects of the same underlying pursuit. Physics seeks to understand the world, and mathematics provides the structure in which that understanding becomes possible. At the deepest level, the two may be indistinguishable. And so the idea that the universe might be a mathematical illusion is not a claim that it is unreal. On the contrary, it is an acknowledgement that what is most real may not be what appears to us directly, but what remains consistent, precise, and unchanging beneath all appearances. What we call reality may simply be the shadow cast by a deeper, perfectly ordered structure. If one continues along this line of thought, the next step is even more unsettling because it asks us to question not just what things are made of, but the stage on which everything appears to exist. We take space and time for granted. They feel immediate and unavoidable. Every experience we have is located somewhere and happens at some moment. It is natural to think of space and time as the fundamental backdrop of reality, something that must exist before anything else can. But there are strong reasons to suspect that this intuition may be misleading. In many of our most successful theories, space and time are not inserted by hand as absolute ingredients. Instead, they arise as part of a deeper structure. When we examine certain quantum systems closely enough, what looks like a continuous space-time can emerge from something that does not resemble space at all. The underlying description may involve abstract variables, algebraic relations, or networks of interactions, none of which carry an obvious notion of distance or duration. And yet, under the Reimagined conditions, these ingredients organize themselves in such a way that a familiar geometric picture begins to appear. This is not entirely unprecedented. In everyday physics, we already accept that many properties are emergent. Temperature, for instance, is not a property of a single molecule. It only makes sense when we consider a large collection of particles and describe their average behavior. In the same way, the smooth fabric of space might only make sense when we look at a sufficiently large and coherent system. At a more fundamental level, there may be no continuous space at all, only relationships that give rise to the illusion of continuity. What is particularly striking is that geometry itself can be encoded in purely non-geometric terms. There are frameworks in which distances, angles, and even curvature are not primary concepts, but instead are derived from more abstract data. The familiar idea of a point in space may lose its meaning entirely, replaced by something more algebraic, more relational. And yet, when we interpret the results appropriately, we recover a picture that looks very much like the space-time we experience. Time, perhaps even more than space, becomes difficult to define in these settings. We tend to think of time as something that flows, moving from past to future in a steady progression. But in a deeper description, there may be no distinguished parameter that plays this role. Instead, what we call time could emerge from correlations within the system. One part of the system changes relative to another, and from this relative change, we construct the notion of temporal order. Time, in this sense, is not fundamental. It is a way of organizing information. There are situations where this idea becomes almost unavoidable. In attempts to reconcile quantum theory with gravity, the usual concept of time begins to break down. The equations that describe the system do not single out a preferred time variable. Instead, they describe a kind of static structure where all possible configurations coexist in a more abstract sense. The familiar experience of time passing must then be recovered as an approximation, valid only in certain regimes. This raises an important point. What we experience directly is not necessarily what is fundamental. Our perception of a flowing time and a continuous space is shaped by the scale at which we observe the world. At larger scales, where many degrees of freedom act together, these concepts become extremely useful and accurate. But as we move toward more fundamental levels, the description shifts, and the language of space-time may no longer apply. There is also a deeper connection between space and information that begins to emerge. In some theoretical frameworks, the structure of space is closely tied to how information is distributed and entangled. Regions that appear close together in space correspond to parts of the system that are strongly correlated, while distant regions correspond to weaker correlations. In this view, geometry is not a fixed background, but a reflection of the pattern of information itself. This perspective offers a different way of thinking about what it means for 2 points to be near each other. It is not about physical distance in a pre-existing space, but about the strength of their relationship within a larger system. Space becomes a kind of map of these relationships, a way of visualizing the underlying structure. It is not fundamental, it is derived. Even gravity, which we usually think of as a force acting within space-time, begins to look different in this context. It can be reinterpreted as a manifestation of how the underlying structure organizes itself. The curvature of space, which in classical theory tells matter how to move, may itself arise from deeper principles that do not refer to space at all. What we call geometry is then a secondary concept emerging from something more basic. One might wonder how such an abstract picture can give rise to the very concrete world we observe. The answer lies in the remarkable stability of the emergent description. Once space-time appears, it behaves in a consistent and predictable way over a wide range of conditions. The laws that govern it are robust, and they allow for the formation of structures from atoms to galaxies. Within this emergent framework, everything appears as if space and time were fundamental, even though they are not. There's a certain inevitability to this. If the underlying system satisfies the right conditions, a geometric description may be the most natural way to organize its behavior. It is not that space and time are illusions in the sense of being arbitrary or deceptive. Rather, they are effective descriptions, accurate, useful, and deeply connected to our experience, but not the ultimate level of reality. This shift in viewpoint has far-reaching implications. It suggests that asking what happened before the universe began may not be a meaningful question because it assumes the existence of time as a fundamental parameter. If time itself is emergent, then the notion of a beginning in time may need to be reconsidered. Similarly, questions about what lies outside the universe rely on the idea of space as a container, which may not exist at the most basic level. Instead, the focus moves toward understanding the underlying structure from which space-time emerges. What are its fundamental elements? What principles govern their interactions? And how does the familiar picture of space and time arise from them? These are the questions that begin to take precedence. As we explore these ideas, we are led further away from the intuitive picture of reality and closer to something that is, in a sense, more abstract but also more unified. The distinction between geometry, matter, and information starts to dissolve. They become different aspects of the same underlying framework, described most naturally in mathematical terms. And so the idea that space and time might be emergent is not just a technical detail of advanced theory. It is a profound shift in how we understand the nature of reality. It tells us that the stage on which the universe unfolds may itself be part of the performance, arising from deeper principles that do not resemble a stage at all. What we perceive as the fabric of existence may be nothing more than a coherent pattern appearing from something far more fundamental and unseen. If one follows this line of reasoning to its natural conclusion, the picture that begins to emerge is one in which the universe is not best understood as a collection of objects, nor even as a stage of space and time, but as a system governed by underlying rules, rules that resemble, in a very precise sense, something like code. Not code in the literal technological sense that we associate with computers, but in the deeper sense of a structured set of instructions or relations that determine how everything evolves. At first, this may seem like a metaphor. We are accustomed to comparing complex systems to computation because it helps us visualize processes and interactions. But in this case, the analogy runs deeper. The fundamental descriptions we use in physics are algorithmic in spirit. They take an initial configuration, apply a set of rules, and produce outcomes that can be predicted, at least probabilistically. The evolution of a system is not arbitrary. It is constrained by consistency, symmetry, and logical structure. In that sense, the universe behaves as though it is executing a set of mathematical instructions. This perspective becomes particularly compelling when we consider how little of the traditional notion of matter survives at the most fundamental level. What we think of as particles are not solid entities. They are excitations of underlying fields, and those fields themselves are defined through equations. The properties we attribute to matter, mass, charge, spin, are not intrinsic in the classical sense. They arise from how these excitations fit within a broader mathematical framework. The identity of a particle is inseparable from the structure that defines it. In this way, the universe begins to look less like a collection of things and more like a network of relationships. What exists, fundamentally, are not objects, but interactions, and correlations. These relationships can be encoded mathematically, and their evolution follows precise rules. The apparent solidity of the world is then a kind of emergent phenomenon, a stable pattern arising from these deeper processes. There's also a striking parallel between this view and the way information behaves. In many areas of modern physics, information plays a central role. It is not just a convenient way to describe systems. It appears to be something that must be preserved and transformed according to strict principles. In quantum theory, for example, the state of a system encodes information that evolves in a highly structured way. Even when outcomes appear random, the underlying process is governed by well-defined mathematical rules. This suggests that information rather than matter may be the more fundamental concept. The universe could be understood as a vast informational structure where physical processes correspond to transformations of that information. The laws of physics then become the rules that dictate how these transformations occur. In this sense, the universe is not made of stuff in the traditional sense, but of information organized and evolving according to consistent principles. One might then ask what distinguishes this view from a purely abstract mathematical system. After all, many mathematical systems exist in a logical sense without corresponding to anything physical. The difference, if there is one, lies in the coherence and completeness of the structure. The universe appears to be a system in which all parts are connected through a consistent set of rules, and where these rules give rise to a rich and stable set of phenomena. It is not just any mathematical system, but one that is capable of supporting the kind of complexity we observe. This brings us back to the idea of emergence. Just as space and time may arise from deeper structures, so too may the appearance of matter and physical processes arise from underlying informational rules. The distinction between real and abstract becomes less clear in this context. What we call reality may simply be the manifestation of a particular kind of mathematical consistency, one that is rich enough to give rise to observers, measurements, and the appearance of a physical world. There is also an important sense in which this view is constrained by necessity. The rules that govern the system cannot be arbitrary. They must satisfy conditions of internal consistency. In many cases, these conditions are so restrictive that they leave very little freedom. The structure of the theory is not chosen at will. It is determined by the requirement that it be logically coherent. This suggests that the form of the universe may be, to a large extent, inevitable. When we look at the success of our current theories, this idea gains further support. The same mathematical structures appear again and again, often in unexpected ways. A concept developed in one area can turn out to be essential in another, seemingly unrelated domain. This kind of unity is difficult to explain if mathematics is merely a tool. It becomes more natural if mathematics is the underlying reality, and what we are discovering are different aspects of the same structure. The analogy with code also helps clarify the role of laws of physics. In a computational system, the rules determine how the system evolves from one state to another. Similarly, the laws of physics determine how the universe evolves. They're not external prescriptions imposed on a pre-existing reality. They are part of the structure itself. There is no separation between the system and the rules that govern it. The rules are the system. At the same time, it is important not to take the analogy too literally. The universe is not running on a computer in the conventional sense, nor is there an external programmer specifying its behavior. The notion of code here is meant to capture the idea of structured, rule-based evolution, not to suggest an underlying machine. The deeper point is that the behavior of the universe can be understood in terms of abstract relations that are precise, consistent, and mathematically defined. As we push this idea further, we encounter a shift in how we think about explanation itself. Traditionally, we explain physical phenomena by referring to underlying mechanisms, smaller parts interacting in space and time. But if space, time, and matter are all emergent, then this kind of explanation reaches a limit. At the most fundamental level, there may be no simpler mechanism to appeal to. Instead, explanation takes the form of demonstrating that a certain structure is consistent, necessary, or uniquely determined by a set of principles. In this sense, understanding the universe becomes more like understanding a theorem than analyzing a machine. We are not uncovering hidden gears and components, but rather uncovering the logical structure that makes the entire system possible. The question is not what the universe is made of, but why the structure it exhibits is the way it is. There is something both austere and elegant in this picture. It strips away many of the familiar intuitions and replaces them with a more abstract, but also more unified view of reality. It suggests that at the deepest level, the universe is not a collection of things, nor even a continuum of space and time, but a coherent system of relations that evolves according to precise rules. And yet, from this abstract foundation, the richness of the physical world emerges. The complexity of galaxies, the stability of atoms, the flow of time, and the experience of observation. All of these arise as higher-level features of the underlying structure. They are not illusions in the sense of being false, but they are not fundamental either. They are the visible consequences of something more basic. In the end, the idea that the universe is more like code than matter is a way of expressing a deeper realization, that what is most real may not be what is most tangible, but what is most consistent and precise. Reality at its core may simply be the execution of a perfectly consistent set of rules.